Welcome to the course Excelling with Mathematical Modeling. Today we will be discussing about the rectilinear motion under variable forces. Now in physics you have already learned that this rectilinear motion which means motion in a straight line. And we know from Newton's law that force is equal to mass into acceleration. And for this acceleration, which is rate of change of velocity, we have the expression dv dt, or this can be written as dv dx dot dx dt. This is rate of change of distance, which is again velocity. So, this becomes v dv dx, or again from here I can write ddt of v is dx dt, which is d2x dt square. So, we have three expressions for this acceleration. One is this dv dt, one is this v dv dx, and another is d2x dt square. Now, let us take that a particle moves in a straight line with a constant acceleration f. So, if it moves in a straight line with a constant acceleration f, we have force is equal to mass into acceleration. So, we write mass into acceleration, that is m into f. The mass cancels and you get dv equal to f dt. You integrate and you get v equal to ft plus some constant. And if you take initial condition, initially at time t equal to 0, the initial velocity is u. This implies your constant is equal to u, and you get the formula v equal to u plus ft. This you have already done in physics. Now, the question is, here it is a constant acceleration f. What will happen if your acceleration now varies? So, it can be a function of f, it can be a function of v, and then how will you solve that kind of problem with the help of mathematical modeling? Well, in physical problems, we have some sort of laws which we have to follow. In this case, this Newton's law, which says force equal to mass into acceleration. So, let us take the change in law. Now, we assume that let f varies as 1 by x. F is the acceleration. Now, it is not constant, it varies as 1 by x. And then your force is going to be mass into acceleration. So, mass and acceleration varies 1 by x. So, some mu by x, where mu is the constant of proportionality. And if we now use the equation, we will have, since this is a function of x, we use v dv dx. This is the acceleration multiplied by mass, and that is equal to the force F, which is m mu by x. So, we state the problem like this, that a particle moves in a straight line with an acceleration which varies 1 by x, or with a force m mu by x in a straight line towards a point O. So, it starts from A and it is moving towards O. Let this distance OA, let it be A, and P be the position of the particle at any time t such that OP is equal to x. Now, as you can see that the particle is moving towards a point which we called a origin, and this is an attractive force. So, if it is an attractive force, this total force will be negative, which is moving towards the origin. If it is a repulsive force, that is, it is moving away from this fixed point origin, then this would be positive. So, this part you have to remember. Attractive force, we have to take this to be negative, and if it is a repulsive force, we have to take this to be positive. So, our equation v dv dx is equal to minus m mu by x. So, this is our model, and we say a particle moves in a straight line and be acted upon by a force F, which is equal to m mu by x, which is always directed towards a fixed point. So, this is your fixed point O, this is from where it is starting, this distance is A, this is the point at any time t, and this point is your variable point x, and it is moving towards O. So, this is the situation. So, now you have to solve this differential equation, and this m cancels. So, you get v square by 2 equal to minus mu ln x plus some constant. So, the initial condition, say initially the particle is at rest at the point A such that OA equal to small a. So, if the particle is at rest, then the initial velocity is 0. So, at time t equal to 0, v equal to 0 and x is equal to a, because the particle is here. If I substitute it, I will get 0 equal to minus mu ln a plus some constant, and which implies constant is equal to mu ln a. So, I substitute the value of constant and you get v square by 2 equal to minus mu ln x plus mu ln a. If I take mu common, it is ln a by x. This 2 is multiplied, so 2 times this is v square. Okay, so this is your step 1, where you have calculated the velocity in terms of the distance. So, it was given the acceleration in terms of the distance, you have integrated, used the initial condition and calculated the velocity in terms of the distance. So, let us now find a relation between the time and the distance. So, I have v square equal to 2 mu ln a by x. Your figure was, this was your O, this is the point A, this is P, such that this distance is A and the particle is moving towards the origin. Now, when you calculate the velocity, this is dx dt whole square is equal to 2 mu ln a by x, by ln means log to the base e, and then dx dt is square root of 2 mu root of ln a by x. Now, when you take the square root, obviously there will be plus minus sign, but then you have to see what is happening. So, you see that with respect to time, whether your distance is increasing or whether your distance is decreasing. So, particle has started from this position and it is moving towards the point O. So, with time your distance is decreasing, and that is why you put a negative sign and you write the distance decreases with time. If it increase, you keep it as positive. So, now you have to differentiate this differential, you have to integrate this differential equation and find a relation between x and t. So, we just use the separation of variables and you will get 2 mu square root dt is equal to dx by root of ln a by x with a negative sign. So, let us ask the question, how much time the particle will take to reach the origin O. So, if you ask this question, let us say t be the time. So, it starts from where t equal to 0 and it reaches here when t equal to capital T. So, from t equal to 0, it is going to t equal to capital T, that capital T I have to find. So, while doing the integration, now you can put from t equal to 0 to t equal to capital T. And when t equal to 0, the value of x is a, because this OA is x, and when t and at the point O, the value of the distance becomes 0. So, here x is equal to a to x equal to 0. So, that will be the limit of integration. Otherwise, you can integrate and then put the values, but this is easier and the first method. So, if you integrate this, this will give you root 2 t, and here you have to substitute. So, this is x equal to a to 0 with the negative sign dx by root of ln x by a, and I will substitute some y equal to either root of this or y square equal to ln a by x. So, let me rewrite this. I will get root 2 mu times t is equal to minus from a to 0 dx by root of ln a by x, where your y square is equal to ln a by x, which I can write ln a minus ln x. So, 2y dy equal to minus 1 by x dx, and from here I can get ln a by x equal to y square. So, a by x is e to the power y square and x equal to a times e to the power minus y square. So, all this will be now substituted in this integral, and also when x equal to a, y is 0, because you put x equal to a here, it is ln 1 which is 0, and when x tends to 0, this tends to infinity. So, you get, if I change everything to y, when x is equal to a, this is 0, when x equal to 0, this is infinite. Now, dx is 2y dy, and this is multiplied by x and also a negative sign which becomes positive the value of x is a e to the power minus y square and divided by root of this, which is y square. So, once you substitute everything, you have this cancelled and you get 2a 0 to infinity e to the power minus y square dy. The easy way of doing this is using the beta gamma function. So, in this case it will be the gamma function, and if you recall, the formula is gamma n is equal to integration 0 to infinity e to the power minus x, x to the power n minus 1 dx. So, this is your value. So, what we do is you substitute z equal to y square. So, dz will be 2y dy and 2 dy is equal to dz by y equal to dz by z to the power half or root z. So, I have a 0 to infinity, this 2 dy will give me dz by z. So, e to the power minus z, and this is dz divided by z to the power half. And you can see when y equal to 0, z is also 0, and when y becomes large, z also becomes large. So, that is why the limit remains the same. Now, to do this, let us put it in the form, in this form. So, you have a times 0 to infinity e to the power minus z, z to the power minus half dz. And I can write this as a times integration 0 to infinity e to the power minus z, z to the power half minus 1 dz. So, if I compare with these two, I get my n to be half. So, a times gamma half. And if you are familiar with this gamma function, then you know that gamma half is root pi. So, it is a root pi. So, you have from here root 2 mu t is equal to a root pi, and therefore, the time taken by the particle to reach the origin is a root of pi by 2 mu. So, that is how you model this kind of situation where the particle is moving in a straight line following some variable acceleration, and you find the velocity, and then you find the relation between the x and t, and ultimately find the time that the particle will reach the origin. Let us now take a second example. Only now I will change this law. So, let me put the force to be some mass times c to the power 5 by x squared to the power 1 by 3. So, the idea is taking such example is that though the force looks so complicated, but as we go on with the problem and the solution, you will see that the moment you follow the steps, everything will fall into places, and it will be quite easy to solve this kind of problem, no matter what kind of complicated expressions are given in the force. So, it is the same situation. A particle is moving in a straight line, moving towards the origin at a distance, say c, and let p be the position of the particle. At any time t. Then our equation of motion will be dv dx multiplied by m, mass into acceleration, which is equal to force, which is again mass into acceleration. So 1/3 means this is 5 by 3, this is 2 by 3. And since it is a attractive force, we just put a negative sign and just write attractive force. And we get our equation of motion. Your m will cancel and you get, sorry, this is v dv dx, sorry, and you get v dv is equal to minus c to the power 5 by 3 x to the power 2/3 dx, and you integrate both sides. So, this will be v square by 2, this is minus c to the power 5 by 3 x to the power minus 2/3 dx, and minus c to the power 5 by 3 x to the power 1/3 divided by 1/3 plus constant. So, you have v square by 2 is equal to minus 3 times c to the power 5 by 3 x to the power 1 by 3 plus constant. And initially the particle starts from rest. And therefore, initial condition initially v equal to 0, x is equal to c, and which will imply the constant is equal to 3 c to the power 5 by 3 into c to the power 1/3, so 3 c square. So, you substitute back, you get v square by 2 equal to 3 c square minus 3 c to the power 5 by 3 x to the power 1/3. Now, if you ask the question that what will be the velocity of the particle at the origin, this distance is c, this distance is x. So, at the origin the value of x is 0. So, if you put x equal to 0 in this particular expression, you get v square by 2 equal to 3 c square. This part vanishes and you get your v is equal to root 6 into c. So, your velocity is root 6 into c, and you take this to be negative because your distance is decreasing with time. So, at the origin this is going to be the velocity. Now, you want a relation between the x and t, and you integrate this. So, you write dx dt whole square, multiply this 2. So, 6 times I take c to the power 5 by 3 common, and if you do that you will get c to the power 1/3 minus x to the power 1/3. So, it is made like that so that it looks a bit symmetrical. So, c to the power 1/3 x to the power 1/3, and if I multiply this here I can see that this becomes c square and this becomes c to the power 5 by 3 into x to the power 1/3. So, your dx dt is negative because your distance decreases with time. So, this is going to be root 6, this is c to the power 5 by 3 to the power half, and this is square root of c to the power 1/3 minus x to the power 1/3. And you write distance decreases with time. Now, you have to integrate. So, separation of variables will give you root 6 c to the power 5 by 6 dt is equal to minus dx by root of c to the power 1/3 minus x to the power 1/3. So, I need to find the time from this point till it reaches the origin, and let that time be capital T. So, from t equal to 0 to t equal to capital T, and when t equal to 0, x is equal to c, and when it reaches here, x is 0. So, it is from c to 0. So, we have to integrate this. This side, as you can see, it will be root 6 c to the power 5 by 6 capital T, and this I have to find out from c to 0 minus dx by root of c to the power 1/3 minus x to the power 1/3. So, let me quickly rewrite this. This is root 6 c to the power 5 by 6 t equal to minus from c to 0 dx by root of c to the power 1 by 3 minus x to the power 1 by 3. In this kind of integration, if you recall, we substitute this, a trigonometric substitution, say sine square x. So, that if I take c to the power 1/3 sine square x. So, that if I take c to the power 1/3, I get 1 minus sine square x, which is cos square x, and then we can simplify. If I differentiate, it is half x to the power minus 2/3 dx is equal to c to the power 1/3 2 sine theta cos theta d theta, and dx is going to be 6 c to the power 1/3 and x to the power 2/3. So, x to the power 2/3 is just square of this, which is, because this is x to the power minus 2/3, it will come to the denominator and cross multiply. So, this is c to the power 2/3 sine 4 theta multiplied by sine theta cos theta d theta. So, if I simplify, this is 6 c sine to the power 5 theta cos theta d theta, and when x equal to 0, theta equal to 0, and x equal to c, sine theta equal to 1 implies theta equal to pi by 2. So, if you now substitute here, you get for c this is pi by 2, for 0 it is 0, your dx is 6 c sine to the power 5 theta cos theta d theta divided by root of c to the power 1/3 1 minus sine square theta. Interchange the limit and adjust the plus sign. So, a minus sign, this will be plus 0 to pi by 2, the limits are interchanged. This is 6 c sine to the power 5 theta cos theta d theta divided by 6 to the power 1 by 6 and square root of cos square theta, so which is cos theta. So, this and this cancels and you get 0 to pi by 2 6 c to the power 5 by 6 sine to the power 5 theta d theta, and here it is root 6 c to the power 5 by 6 and t. So, this and this will cancel and we write this one more time. Root 6 times t is equal to 0 to pi by 2 6 sine to the power 5 theta, 6 sine to the power 5 theta d theta. Now, you have to now solve this. The easy way would be that you write this as 6 0 to pi by 2 sine to the power 4 theta sine theta d theta. And then you substitute. So, you have to substitute in such a manner such that if you differentiate, you get sine theta d theta, and the easy way is 1 minus cos square theta and whole square of that, such that this becomes sine square theta square it sine to the power 4 theta. So, you substitute z equal to cos theta and dz is sine theta d theta. When theta equal to 0, z equal to 1 and theta equal to pi by 2, z equal to 0. So, you get this is 6 times 1 to 0, 1 minus z square whole square dz. Now, this is easy to integrate, and if you find the value, you will see. So, this is root 6t, this and this gives you root 6, and if you integrate this and find the value and simplify, you will get your t to be 8 by 15 root 6. This I leave it to you. This is quite easy to integrate, and so the time taken by the particle from A to reach the point O is 8 by 15 root 6. So, with this example, we come to the conclusion to how to deal with the motion in a straight line or rectilinear motion where your acceleration is a variable quantity. So, in our next lecture, we will be doing about this dynamics of rowing, which is again an interesting area of modeling. Till then, bye bye.